Yeah, so I saw quickly in the chat when I hopped in, some people said they got 108. Did other people get 108? Is that true or is that not true?
I got 192.
All right, we got two choices now, 108,
I got 90.
90, we got three choices. This is getting better and better.
I got negative 204.
Four choices, negative 204. I'm loving it.
I got 92, but I might have done the negative and got 108. I got to double check that.
Yeah, I also got 92.
Yeah, now, does it bother you that the purple graph is like under the x-axis now? Like this is going to screw things up, right? Because now it's like the area under the green graph plus the area under the purple graph, or absolute value, or did the graph, maybe this was what Eve was talking about going out the door, does that bother you like that it was like that?
Yeah.
So let's just think for a second here. Well, the green graph is the y coordinate is, that didn't help because it's lagging behind still. The height there is y1, right? And this height down there is y2. So what do you have to, like, I got to add them together, right? I got to add y1 and y2 to get the height, don't I?
I accidentally messed up a negative sign. I actually got 108.
Okay, so we have 2 for 108. Do you agree that on the purple graph, y2 is negative there? Like y2 would be a negative number since you're going down? For that reason, y1 minus y2 still works because it's negative. So if y1 minus a negative y2 actually becomes y1 plus y2, nothing is new. The fact that it's under the x-axis doesn't make any difference. You can ignore it. I mean, that's amazing.
Yeah. See, I don't know if I had graphed it, that might have made sense, but I was looking at it and I don't know. I think I did it backwards.
So the green graph is indeed up on the top, and some of you did this wrong. What is that person screwing up?
They forgot to distribute the negative sign.
Yeah, it's minus everything. Does that make sense? So you got to be careful with that. So negative x squared minus 2x squared is minus 3x squared. 3x minus a minus 9x is actually 3x plus 9x. And 7 minus a negative 8 is actually 7 plus 8. And so that's what we just did a second ago. The question is, does that still work? And is that what you did? Now notice I cheated on Desmos again, and Desmos told me where they intersected, and they intersect. And notice again, we're working with x values. And therefore, what am I interested in? Well, I'm interested in that x value and that x value. I don't care about the y being negative 3 and positive 3. I care about x is negative 1 and x is 5 because I'm working with x's. Again, that's the substitution concept. So negative 3, that becomes x cubed divided by 3. The 3's cancel, so I get negative x cubed plus 12x squared divided by 2 is 6x squared plus 15x. Is that the right? It's just, and again, this is not a hard integral, thank God. I'm working on the concept here.
Yeah, it is. I ended up with the inverse of that.
You had positive signs where I had negative signs?
Yeah, exactly. Yeah. And I think that's because I subtracted y1 from y2.
Yep. And the cool thing is if you get that backwards, and this is indeed 108. If you get that backwards and you get it right, you get negative 108. And then you just say, oops, I must have subtracted wrong. So you should never get a negative answer to these problems anymore, which again, I think is cool because remember, in the real world, there's no such thing as a negative area. So You're never going to get a negative answer if you kind of get this right. As I said, if you get this backwards and you get negative 108, just write, oops, must have subtracted wrong, and then write 108. Like, don't do it over again.
Hey, Doug,
Yeah.
I have a question. Since the parabolas don't meet on the x-axis, wouldn't that mess up the area?
Yeah, I love that. Good question. So let's stare at that picture for a minute. So that is not so straightforward. So I love your thought there. Let's stare at that for a second. First of all, does everybody understand what Julian just said?
Something tells me that it doesn't really matter if they meet on the x-axis, because when we had a discussion about negative area, so to speak, we said it's not truly related to the graph. We just move the graph so it fits our area. Are you following what I'm saying?
Yeah, I think I am.
So for the axis, for the y-axis, I think it's the same thing. It doesn't matter so much. That just is the area. And yeah.
So I just shaded in the area, and I want you to visualize it while we're waiting here. I got to figure out how to solve this. I just shaded the area under the green curve, but do you notice some of the green curve is above the x-axis and some of the green curve is below the x-axis?
Isn't it 92? No. Oh, never mind. Never mind.
So do you agree that part of that is positive and part of it is negative? Now remember, what you're getting when you just type in -1 and 5 is you're getting the net area. So actually part of that area is positive, part of it is negative, and you're getting the sum total of that. I mean, so if you were to do this separately, you'd be getting this positive area and that negative area combined. So you wouldn't have noticed it, I guess is what I'm saying. You would have just typed in under the green curve, found its area. And then notice the same thing kind of happens with the purple curve. I guess I won't draw it in just in the interest of, oh yes, maybe I will, because that might teach us something. If I go to that purple area, the area under that purple curve, well, here's the easy part. Notice this is all positive, but then what about this part right here? Do you notice I end up shading that part twice? I shaded the exact same part twice. And they're both negative, aren't they? Well, if they're both negative and you subtract them, like -8 minus -8, 0. -6 minus -6, 0. Like those are canceling. Do you see what I'm saying? And the same thing is happening over here. That little chunk of area is positive in both cases. So those are going away. Do you see that? So it does work. That's a great question. It didn't occur to me to even ask. But this is kind of cool as a shortcut. But again, the beautiful thing about this is what you're really doing is by subtracting them like we're doing rather than doing them separately, we're really just finding all of those rectangles where there is no space. There is no area under a curve anymore. It's just this, how tall is that rectangle? Y1 minus Y2. So the rectangles only exist in that little kind of eyeball of space that we're looking at.
Hey, Doug, I'm just having a little trouble picturing. I did it all right because, you know, Y1 minus Y2, basically. But if we wanted to get that whole area, I'm wondering why we're not doing Y1 plus Y2.
Because Y2 is negative. Since that graph is underneath there, it's negative. And so if you add them, you're going to get a teeny short rectangle that is not as tall as the shape.
Okay, that makes complete sense. I was just wondering it this whole time, trying to picture it, but that makes complete sense. Thank you.
Nice job. It's a great question. Notice it
Yeah,
was
I'm glad you asked.
nice job. Notice it was kind of obvious to subtract them. Oh, geez. It was kind of obvious to subtract them here because it was a positive y and a positive y. So we would subtract them to get that height. But it's much less obvious when one of them is actually negative. But isn't it cool that if you subtract them, it still works? Like you don't even have to think about it. You just go top one minus bottom one every single time. And when the bottom one is negative, when you subtract them, turns it into a positive. And then you are adding them. So you don't, it's like the automated process takes care of itself. You don't have to think, okay, this one's down, so I got to think of it as negative, and then it's an absolute value, and now I have to add it. Like you could do that, but you don't have to. Isn't that cool?
Yeah, I was tempted just to keep going and just say y1 minus y2, but I was scared that you were going to throw just a picture on the test like you did on the first one, and I was going to get all screwed up.
Yeah. Well, and what's amazing about math is it takes a little bit more time, but you can understand it. Like you can reason. I love the clarifying questions you're all asking, and that's why we're taking 2 days with this. It's such an important topic. We're going to take kind of a whole nother day and play with this concept just because I want you to see it. Let me show you something cool. A couple cool things, actually. I wasn't just sitting there making coffee while you were gone, my friends. I was doing stuff. Notice something cool in Desmos. So I came back knowing the correct answer to this problem, thanks to Desmos. Notice I just said y, like, do you see it in action here? I mean, isn't that cool? F of x minus g of x, y minus y. And so I typed it in and she didn't got the answer. I mean, isn't that awesome? Now let me show you something even cooler. You're thinking, that's impossible. There can't be anything cooler than this. Well, I'm afraid there is, my friends. Trying to remember how to do this. Now that
Could I ask a real quick question?
Two things. Go ahead. I heard Eve, and I think I heard Justin. Go ahead, Eve.
What kind of application would be for this?
Well, what this does is just opens the door to real shapes now. Does that make sense? In other words, if somebody had like a football kind of a shape, I paid my way through college punching football shaped holes out of plywood, punching a knot hole out and plugging it back up with a good piece of wood. And so there's this little football shape. So looked like an eyeball, looked very close to what you're looking at right now. And so, you know, that's an actual shape. And so what's the area of that shape? Well, now you can answer that question. I mean, that's where it starts.
Okay.
Like, so for now, let's just think of it as geometry. So from now on, if you look out and you see some weird space and you think, well, hey, I could define the top of that with one curve and then the bottom that with a different curve, then you could actually find the area now. So to me, it just left the piece of graph paper today, and now it went out into the real world. That's kind of what I'm getting at. So I'm just gonna, just because it's fun, I'm gonna show you how to shade this now, how to actually shade the area that we're describing in Desmos, just because it's kind of fun. If I go in and I say y is less than or equal to, so I want to shade under the green graph. So now I'm just going to type the green graph. If I was doing this on my computer, I'd be just saying copy, but I can't seem to do that on here. Maybe it's because I'm low skills. So that's kind of good, right?
Could you not just type in f of x?
Yeah, but couldn't I, that actually just occurred to me too. Since I already typed it, couldn't I just say f of x for that? Yeah, apparently I can. But notice it shaded forever, right? And I really wanted it to stop at -1 and 5. And I have showed you before how to go up here and stick some brackets around this. Bracket, let's see, I want to say between -1 and 5. So I want to say greater than -1. I want x to be greater than -1. times do I have to hit that? And less than 5. So I just limited the domain of the green graph. Now, the second thing is I really would like this to go, I don't want it to go down forever. Does that make sense? I'd like it to stop when it hits the purple graph. So
then you would just type g of x is less than y, right? At the beginning of that.
yeah, so I think,
Or less than or equal to.
I think I can come down here and say, oh, and by the way, I would like the y value to be greater than, g of x. It worked. I'll copy this into the notes so that you can. Now, again, does that really accomplish anything? No, but it's just kind of cool. And if you wanted to, you could go back and, limit, and I wish I could copy right now. I could limit the purple graph as well, like not let it go forever. So also say from -1 to 5. So that's kind of cool, right? And remember, just for the fun of it, if you can shade, unshade, you can go to that little gear up on the top and you can say, I don't like red, I like green, stuff like that. So to your point, Eve, this is kind of what I mean. Like in the real world, you might see a shape like that. Now it'd be up to you to say, well, I can take some measurements on that green curve and find a parabola that models it. That's no joke. Like that'd be difficult to do, take regression to do it and so forth. But now it's not on graph paper anymore. Does that make sense? You're sort of using the graph paper to get an answer, but you're actually finding real shapes. And you can probably appreciate, and this is what we'll spend a little bit more time with tomorrow, that this isn't limited to 2 curves. Like, could you have 3 curves that it takes to define a shape? Yeah, you could. Or 4 or 6, yeah. So just so that is in the notes, let's get it over here.
So you mentioned we'd be taking this into 3 dimensions eventually.
Yeah.
So like we'll be finding the volume of a shape like that.
Yeah. Now, if that shape just went straight into the page, it'd be easy because you just find the area times how deep into the page it went. But what if coming towards you, it was even curved? Do you see what I'm saying? If it's coming towards you and it's curved, that's Calc 4 in the summer, vector calculus.
Yeah. That's what I was wondering, because like we don't really know what shape that shape is. So
exactly. Yeah. And so this we're living in a 2D world here. Like we're doing 2-dimensional calculus, and Calc 4 is 3-dimensional calculus, where that even has an equation that defines how it comes towards you and away from you, which sounds terrifying, but it's just doing it in one more dimension. Like there's no new calculus to learn there, interestingly.
Yeah, I was typing in the same thing into Desmos, and for the when you were isolating the shading, you can also, like at the bottom there, instead of putting y is less than g of x in brackets, you can just put g of x at the beginning with a less than y, less or greater than f
cool.
of x.
Everybody understand what Justin just said? Like what I typed was a little cumbersome. He just sort of said y is between f of x and g of x. That's cool. I didn't know that.
Yeah.
I'm surprised it.
I mean, I figured it would work because of how everything else was working, and so I just typed it in there, and it worked.
Awesome. I love it. Good job. I learned something new today then. Let's see. So this is pretty powerful. So as I said, kind of and I would encourage you to do this. As I said, I want this class to ruin your life in some respects. There's most geometrical shapes that humans make are the simple ones, like circles and rectangles. honestly, that takes care of 90% of things. If you look out your window, 90% of things that you see are going to be straight lines and circles. And straight lines create rectangles and triangles, and we have geometric formulas for all that stuff. You can appreciate if somebody wanted to, you know, build that part out of metal, that's going to cost more money. Like, you better really want that shape. Like, if that's the logo for your business, now you're going to write something inside there and make that cool sign hanging out off your building and stuff. You better really want that, because it's going to cost you a lot more than saying, make me a rectangle. So you don't see it that much. And also, you know, like, you got to know a lot of math in order to be able to deal with things like that. But as I said, if you take a circle here and a circle here, that shape right there is what I paid my way through college, cutting out of plywood, these little sort of football shapes. So those are actually both circles in this case. Does that make sense? In our case, we just did it with two parabolas, but that's with two circles. And so that's a shape you can see occasionally. It looks like a football. So you can now do that. And that would be hard. Like, even though that's a circle and you say, hey, I know the area of a circle, I would challenge you, and I guess I'll say this for extra credit because it just occurred to me. Could you find some kind of a formula for that? If these are both radius r, like, I'll make it easy on you. They're not even two different radiuses. Could you find a formula that would figure out what that area is just based on regular pi r squared? And I actually don't know the answer to that. It just occurred to me. As a function of, like, how much do they overlap? Does that make sense? So maybe, and this is why algebra is cool. Do you understand this statement? Can you find area as a function of r and h, like a formula? So first you got to pick a radius, and then you got to decide how much do the circles overlap. That's a variable. And so can you come up with a formula for that? And does it make sense, by the way I wrote that the formula is going to have r's and h's in it? And so the answer is, it could be done, but maybe it's terrifying. It could be done. Maybe it's actually quite easy. Maybe it can't be done, in which case you actually have to have calculus. That's a pretty interesting extra credit question, I would say. And as I said, I don't know the answer to it. But you can at least appreciate somebody wanting to know, right? Like, if I'm the one designing this at the mill, you know, why did they punch the holes out of the plywood? Why did they punch those out with a football shape? Why not just a circle? I don't know the answer to that, but at some point there was somebody thinking, and, you know, you can appreciate somebody wanting to know the area of that thing. So how does that work? I will tell you, in construction, with respect to an application, I have been asked by more than one framer, because it's so freaking hard, that wants to build an arch in a hallway or over a window or something like that, but the arch is not a half circle, it's a portion of a circle.
Yeah, I was gonna say, do you think it has to do with the arch
And
being more stable?
hard. That's very hard, it turns out, to kind of figure that out. Because the framer might know, for instance, this is 10 feet wide, and the designer might have decided to make that, say, 2 feet tall. And that might be all you know, because you drew that picture. Hey, I want to make an arch that looks like that. It's a circle. But you can't make a circle unless you know the radius. And so I've had more than one framer ask me, hey, if I know it's 10 feet wide and it's 2 feet tall, how can I figure out what the radius is? That's also a very damaging problem. Now, it isn't a calculus problem, so this is something I give for extra credit and as a project in lower level math. But for those of you curious types, I've just ruined your life right there by giving you two interesting problems. Hanging, I mean, I guess I would give you extra credit for the second one too, even though it's not a calculus problem. Just if you do take the time to do it, I'd like to give you some credit for doing so. In this case, I would say find the radius as a function of the width and the height So don't use 10, use W, don't use 2, use H, because you want a formula. This is what people do in math. You want a formula that works every time. You don't want a formula that just works for 10 and 2. You want it to work every time. So can you do it for in my case, math has come up very randomly, just as a result, as I said on the project the other day, as a result of asking interesting questions. Seems like there would be some way to find the radius of that circle. Seems like there would be some way to find the area of that football shape. So cool. Let's see, where do we want to go to from here in the interest of time? I don't think I need to show you anything new. I think I'll kind of tell you. I'll tell you something about tomorrow. I'll just give you some introductory thoughts on tomorrow. We're going to look at some curveballs tomorrow, like expand our mind a little bit. And there's sort of two things that I want you to think about. One of them is this. We'll just use the same shape we had a second ago as an illustration. What if I added a third equation to this? And let's just kind of just throw it in there totally randomly. Like, whoa, wrong. So I just drew that line through it. And now what I would like to know is this area. Let's try shading it. That sounds like fun. What if I gave you 3 equations? So I want to know the area above that line, above the red line, below the green parabola, above the purple parabola. I shaded that, but it's going to take a second to show up apparently. Is that different? Be brave and propose. You haven't thought about this very long. I'm not looking for the right answer. I'm just looking for what mathematicians a conjecture, which is an educated guess. Let's just discuss it first.
Since we already found the area of that shape, I suppose, then can't we just subtract away the area behind the line? And that will give us that area of the shape. We just take the area of the shape and subtract it from the area of the line.
So Eve is saying, since we already sort of know the green areas, there's something we could do there to kind of save time. Does it make sense if you knew the green area, the original green area, then you'd have to come back and subtract that area on the bottom off to get it? Which is kind of the same problem. It's still a space, it's still a shape, but now it's not defined by just 2 curves, it's defined by 3 curves. And one of them is a line, but generically we're calling them curves. Does it still work? Is like, I mean, where are the rectangles? If you draw the rectangles in, what do I subtract? I got 2 equations now. So for 3 equations, how do I subtract them?
You'd have a different level of limits of integration on that line than you would on the other 2.
Yeah, like notice this point over here is not even in the picture anymore. This one still counts. But this one over here, we don't even kind of need anymore. And we're certainly going to need, these points now. Does that make sense? We're going to need to know where those are. But draw the rectangles in your mind. Like, is this different than before? How do we expand our mind or our thinking to accommodate this? Do the rectangles still work? Like, imagine rectangles going all the way across this, like a Riemann sum.
I'm thinking it would still work. It would just be a little bit more complicated because you have 3 equations you're putting together.
Yeah. Do you understand that there's a very important demarcation, right? How fat is this line? Ooh, that's exciting. That's huge. That's too big. Do you understand that? At least visualizing it, that line is really important right there that you can't see. Try to fat line. It's too fat. Do you agree that on this side over here, it's kind of the green equation minus the red equation? That's what's going to give me my heights of my rectangles. Whereas over here, it's green minus purple. It's no different. Now, you're not going to see many problems, if even any problems like this, because all this is doing is it just made this double the work without knowing any more calculus. Does that make sense? But my point is if you, again, look out the window and you see, hey, there's a cool shape and it's defined by 4 different curves, it might take some time, but the key is which one is above, which one is below. Does that make sense? That's what defines the rectangle. So you've got to picture this. That's why we drew this before. The green curve is above the red curve. Oh, well, then if I go green minus red, that'll give me the height of those rectangles. The green curve is above the purple curve. Okay, well, if I go green minus purple, that'll give me the height of those purple rectangles. And so this is 2 separate problems. You can't do this all at once. There isn't a way to do this all at once. But it's not really new. Second thing that I'm not going to answer today is easy. 2 problems. So this is the first curveball. What about the second curveball? What if I gave you 2 parabolas, except for, actually, I think I'll give you a parabola and a line. What if I asked you for that area? Is that a new problem? Does it matter that, and you may remember from parabolas that are up and down are y equals x squared. Parabolas that are sideways are x equals y squared. So that's the way that parabola wants to, that's the way that equation might be written down. Remember, Desmos has no problem with this, but your graphing calculator is going to have a problem with this. How am I going to find that area? That's the question. And that'll be the main thing we kind of tackle tomorrow. Any thoughts on that?
Would you subtract the x values from each other instead of y? I don't know.
I like it. Conjecture. So you're thinking, can I subtract sideways or something like that?
Yeah, I'm just like, but I don't know. I don't even know how that would work.
Yeah, that's what mathematicians do. You make conjectures. You say, I don't know, would this work? And you don't know the answer to that. That's what makes math fun. Does it make sense if I chopped it just like I did the previous problem, kind of right there? On the right side of that, I have purple minus orange. But then on the left side, I have like orange minus orange. So that feels weird. How am I going to find that? So that's one of the main things we'll tackle tomorrow. This question up here is actually not new. You already know it. It's just more time consuming. This question is kind of, the second one is kind of new. So given that I got off and got back on, I'm not really sure what happened to the recording for today. I don't know if there's like two separate recordings with a big gap in the middle, or the second one didn't record at all. I have no idea. But you're here, so I'll post these notes and that'll mean something to you, and we'll go from there. So there's many questions, and I would very much encourage you to do this, like wade into the 6.2 assignment. The questions that have X equals with a bunch of Y's on the other side, you sort of won't be ready for those. But most of the questions in your assignment, I would say the top 2/3 of them, I think there's 12, the top 2/3 of them you can do right now, and that'd be really good practice. But again, take your time, visualize it, picture it, draw it in Desmos, cheat, make sure you know the right answer, not just to check your work, but to actually visualize the problem. It doesn't take that long to type it into Desmos and play around a little bit with some of the features in Desmos that allow you to, shade it and so forth, and draw your own pictures on it and things of that nature. Anything else? All right, adios. I'll see you tomorrow. Stay after, as always, if you would like.